We expect modern infrastructure to function exactly as designed, but look at this split screen. On the left is the pristine, meticulously engineered layout of Kansai International Airport. On the right, that same engineering marvel is completely incapacitated, drowning under a massive storm surge. To understand how this happened, we have to look at the sheer scale of the project. Kansai is an artificial island measuring 4 kilometers long and 1 kilometer wide. It sits far off the coast in the deep waters of Osaka Bay, constructed by dropping 21 million cubic meters of fill into the ocean. The engineering behind this island creates a fascinating paradox. In 1995, the Kobe earthquake struck just 20 kilometers away. The airport absorbed the massive seismic shock and suffered zero structural damage. Yet 2 decades later, a severe weather event completely neutralized the facility. In 2018, a storm surge peaking at 5 meters breached the island's coastal defenses. The water flooded the runways, inundated the cargo facilities, and left the main terminal stranded in the middle of a temporary ocean. Kansai serves as an extreme case study in dynamic infrastructure. To understand its survival and its failures, we have to analyze 3 interlocking systems that are in constant motion. The flooding was the inevitable mathematical collision of soil mechanics, structural kinematics, and shifting climate baselines. The ground beneath Kansai is a thick, highly compressible layer of saturated Pleistocene clay. To stabilize it, engineers drove millions of vertical sand drains into the seabed, then added massive weights of earth on top to physically force the water out of the clay. Based on traditional linear soil models, specifically end of primary or EOP consolidation, engineers predicted the island would settle between 11.6 and 12 meters over a 50-year lifespan. The reality exposed a severe limitation in those linear models. By 2018, the island had rapidly surpassed 14 meters of settlement, and it was still sinking. The data demanded a different mathematical framework. Geotechnical engineers turned to Juarez-Badillo's principle of natural proportionality, a model designed to capture the complex physics of ongoing secondary compression in soils. This nonlinear time settlement equation isolates a specific variable called the fluidity coefficient, or delta. Delta maps the transition of the clay, treating the subsoil as an actively compressing fluid throughout its life cycle. Applied to the Kansai data, the end of secondary settlement curve diverges completely from the original 12-meter prediction. Projecting this asymptotic curve forward into infinity reveals the expected settlement. The island will sink 19 meters. Treating the ground beneath a marine megaproject as static guarantees failure. The earth beneath Kansai is a mathematically dynamic fluid, requiring infrastructure that can move with it. Sinking 14 meters into the ocean is a problem, but it is compounded by differential settlement. The island does not sink evenly. If you place a static concrete foundation on ground that sinks faster on one side than the other, the shear forces will tear the concrete apart. Architect Renzo Piano recognized this threat. His design philosophy relied on severing the stability of the terminal building from the ground it rests on. The mechanical solution rests in the substructure. The entire terminal is supported by 900 independently adjustable columns. As clay compresses, sensors monitor the foundation. When a specific sector drops, the building registers the discrepancy. Crews insert hydraulic jacks into those columns, extending them to push the superstructure back to a perfectly level plane. This design transforms the terminal from a passive structure into an active, self-correcting machine, engineered specifically to survive a collapsing foundation. Adjusting terminal height doesn't solve external threats. As the island settled 14 meters, coastal defenses sank with it. Dropping 2 meters past the baseline eroded the seawall's critical freeboard, the physical height keeping the ocean out. This infrared satellite image tracks the approach of Typhoon Jebi in September 2018, moving directly toward the compromised defenses of Osaka Bay. The storm hit the coast with extreme meteorological force, dropping to a central pressure of 915 hectopascals and generating sustained winds of 105 knots. These forces pushed a 5-meter storm surge directly into Kansai. The original seawall could deflect this volume of water, but the sunken seawall did not. The breach immediately halted operations. The surge completely submerged the air cargo area and inflicted severe physical damage to the 3-kilometer access bridge connecting the island to the mainland. This chart maps the timeline of operational recovery. Passenger and cargo operations were suspended for extended periods, resulting in direct economic damages to the Kansai region, estimated at 60 billion Japanese yen, or 0.3% of the region's entire GDP. The disaster proved that infrastructure built on sinking land faces a compounding threat matrix. Day one design specifications become obsolete as the physical elevation drops and severe weather events intensify. In response, the airport operator completely revised its business contingency plan. This required abandoning historical averages and integrating new projections from the Intergovernmental Panel on Climate Change regarding future sea level rise. This flow diagram outlines the rigorous engineering process required to develop a new infrastructure resiliency strategy, moving from defining the specific water level and wave height impacts down to evaluating the remaining acceptable risk for the facility to prevent future overtopping. Engineers modeled two competing defense strategies: raising the height of the seawall alone versus raising the seawall while simultaneously elevating an array of outer tetrapods. The math comes down to the overtopping rate. Japanese standards for a 50-year return period demand a maximum overtopping rate of 0.02 cubic meters per second. Modeling showed only the combined seawall and tetrapods could sufficiently break wave energy to meet this strict threshold. This translates theory into concrete reality. The interlocking mass of the tetrapods disrupts the storm surge's kinetic energy before it reaches the primary wall. A robust resilience strategy requires defenses engineered for extreme scenarios, exceeding current standards and historical maximums. Kansai's soil mechanics, structural kinematics, and coastal defenses now operate as one unified model. As the ground sinks toward 19 meters, hydraulic jacks actively mediate between the collapsing foundation and the rigid terminal. Simultaneously, the island evolves its perimeter defenses to block a hostile ocean. Civil engineering megaprojects can no longer be built as static monuments, fixed in time the day the concrete dries. Surviving the physical demands of the 21st century requires continuous empirical observation and the willingness to physically alter infrastructure mid-life cycle based on new data. Kansai Airport proves that human engineering can adapt to almost any planetary force, provided we stop treating the ground beneath our feet and the climate above our heads as constants.